Okay. Chapter 14, question 14. This is a problem solving about deduce a rate law. Okay. Starting with the data in table 14.1, I just wrote on the board. This is 14.1 table. A, deduce the rate law for the reaction. B, calculate the rate constant K. C, calculate the rate of the reaction at the time when F2 concentration 0.01 and ClO2 concentration is 0.02 molar. Okay. So let's do A first. Deduce rate law. Okay. How to deduce rate law? The rate law looks like this equation shows, right? So for K times the fluorine concentration raised to X's power times ClO2's concentration raised to Y's power. So first of all, our job is to figure out X and Y. Okay. To fix X and Y each time, we can only fix one, figure out one. Either start with X or start with Y. Okay. So X, this is the reaction order respect to fluorine, right? So if we want to figure out X, then ClO2's concentration should keep constant, no change, right? So Y can be cancelled, only left over X. So take a look at this table. Which experiment? Let's label this experiment 1. This is 2. This 3, right? This means if we run experiment 1, number 1 experiment is F2 concentration 0.1, ClO2's concentration is 0.01, and we find the initial rate V is 1.2 times 10 to the negative 3. Second experiment is F2 concentration same, didn't change, but ClO2 concentration 4 times higher. Then this time we find the rate becomes 4.8 times 10 to the third power. 4 times higher, right? Experiment 3, so this time compared with 1 is F2 double the concentration, while ClO2 concentration didn't change, and rate becomes 2.4 times 10 to the third negative third power. Compared with 1 is double, right? So if we want to start with X, then we need to choose 2 experiment with ClO2 concentration no change. In this way, Y be constant, right? So clearly you need to choose 1 and 3. ClO2 concentration no change, same, right? So choose experiment 3 compared with experiment 1. F2 concentration doubled, while ClO2 concentration same. So Y be cancelled, only left over X. So we use V3 over V1. V3 means the rate in experiment 3. V1 means initial rate in experiment 1. Okay. So in this way, is K times V3 F2 is 0.2, right? 0.2 raised to X. ClO2 0.01 raised to Y's power. Okay. While we want K times F2 is 0.1. ClO2, sorry, this ClO2 is 0.01. Right? So in this case, CaO2 concentration from F2 and F3 and F1, they're exactly the same. So this can be conserved. Right. And K also same. K depends on temperature. No temperature change. So K should be same. Still not very good. So in this way, only left over 0.02. Not 0.02, it's 0.2. 0.2. Denominator 0.1. Both x to the power, so we can combine it together as x to the power, right? Well, according to this table, V3 is 2.4. So 2.4 times 10 to the negative 3. V1 is 1.2. Equal to 0.2 over 0.1 x to the power. So you find 10 to the negative 3 is the same. 2.4 divided by 1.2 is 2. Right? 0.2 divided by 0.1 is 2. 2 to the x to the power. Is this clear? X is 1. Right. 2 to the x to the power equal to x equal to 2. Of course, x is 1. You get it? But compare with experiment 3 with experiment 1, we figure out x. Then, which two experiments we need to choose to figure out the y? To figure out y means you need to let these two experiments F2 concentration the same, so x can be conserved. While CaO2 concentration varied. So clearly only these two. F2 concentration same. CaO2 concentration varied. So we choose experiment 2 with experiment 1. Experiment 2, F2, 0.1. CaO2, 0.04. Experiment 1, F2, 0.1. CaO2, 0.01. Raised to y. So this time, K, same. Right? K is rate constant, only depends on temperature. No temperature change, K is same. And F2 concentration in experiment 2, in experiment 1, exactly same. Right? So these two can be conserved. So X conserved. Only left over Y. So this both Y's power. So we combine it together. It's 0.04 over 0.01 together. Y's power. And according to this table, V2 is 4.8 times 10 to the negative third. Experiment 1 is 1.2 times 10 to the negative third. Right. Now we just simplify this. Negative 10 to the negative third power is 4.8 divided by 1.2 is 4. So simplify as 4 equal to 0.04 divided by 0.01 is 4. to the y's power. Then clearly y is 1. Right? So y equals to 1. Okay. Are you okay? Okay. So this is a first step. Deduce the rate law. We figure out x and y. Then times k is a rate law. So rate law is V equals to K times F2 raised to X's power is 1. And ClO2 raised to Y's power also 1. So this is the rate law. Then second step, ask you, okay, sorry. So first is deduce rate law A, right? Second is ask you calculate the rate constant K. Okay. How can we calculate the rate constant K? So we can pick any experiment data. Let's pick experiment 1. So V1 equals to K times F2 and ClO2, right? This is rate law. And what is V1 value? 1.2 according to this table. It's 1.2 times 10 to the negative third. K, what is F2? 0.1, right? Just take a look at table 14.1. ClO2, 0.01. So K equals to 1.2 times 10 to the negative third divided by 0.1 and 0.01. Okay. Then clearly it's 1.2. These two cancel this negative third power. Unit is a second order reaction. So unit will be per molar per second. Okay. In last class, we shared the homework number 8. The unit for K. First order reaction is per second. Second order reaction is liter per mole per second, which is per molarity, because molarity is mole per liter, right? So per molarity means liter per mole per second. The second order reaction. Okay. If we choose experiment 2, then similarly, still this rate law. Just plug in the experiment 2's data. So V2 is 4.8 times 10 to the negative third. K times F2 is 0.1. ClO2 is 0.04. So K is 4.8 times 10 to the negative third divided by 0.1 and 0.04. You find it's the same. Choose experiment 2, you get the same answer. If we choose experiment 3, it's still same. We actually don't need to rewrite this. Just plug into experiment 3's so value is 2.4 times 10 to the negative third. K times F2 is 0.2. ClO2 is 0.01. And K equals to 2.4 times 10 to the negative third. It's V3 divided by F2 concentration and ClO2 concentration. Same. Most case, if we run experiment, will not be so perfect. The 1.2, 1.2, 1.2 exactly the same. Most cases will be pretty close to the same value, like 1.19 or 1.21, whatever, very close to 1.2. Here is not actual experiment. I believe it's just for you to problem solving, not that. This number not from actual experiment. Okay. Just as a Chem make things easier, we just create a number, give you exactly the same. Again, if run actual experiment, the K you calculated pretty much not exactly the same, but very close to a value, then this is a rate constant. So since this rate is the same, then average still this value, right? So rate constant K is 1.2. If these three calculations not exactly the same, then you need to calculate the average. Report the average K. This is B. And C. Calculate the rate of the reaction at the time when F2 is 0.01 or ClO2 is 0.02.
On the quiz, are you going to want us to calculate all three of them, like for every experiment? In case
Yeah, read my statement. Okay. Normally is three calculations. The result will not be exactly the same. Then you need to calculate the three and get average value of K.
Okay.
The method is the same as here, which are okay. C asks you calculate the rate of the reaction when F2 concentration 0.01, ClO2 concentration 0.02. So F2 concentration 0.1 and ClO2 concentration 0.02 molar. No, F2 concentration is also is 0.01, not 0.1. ClO2 concentration 0.02, not listed in this table. Otherwise, you already calculate, you already have, right? So when these two rate and concentration tell you, then we can use this rate law together with the K we just calculate. We can figure out the rate. The rate will be K times F2 and ClO2 concentration, right? This is the rate law. And K we just calculate all three 1.2, then average is still 1.2, right? So 1.2 per molar per second times F2 is 0.01 molar. ClO2 0.02 molar. Then just use your calculator. 0.01, 0.02. 2 times 1.2 is 2.4. Then exponent 0.01 is 10 to the negative 2. This also 10 to the negative 2. Right? 2, this 2 we already combined it with 1.2. So 10 to the negative 2, 10 to the negative 2, total 10 to the negative 4. Right? The unit, this molar consider this 1 per molar. Leftover 1 is molar per second. Yeah. Molar is the concentration per second is the rate.
What number is this?
Question number 14. Chapter 14, number 14. Okay, are you okay for this? Again, kinetics part need a lot of math calculations. You need to spend more time during the weekend. Okay, if you're okay, then we can show you another one. Do you have a question for this? No. Okay, then let's show you another one. Let's take a look at number 24. Number 24. Rate constant for the second order reaction 2NO2 gas breakdown itself becomes 2NO gas and 1O2 gas. This is the second order reaction. And the rate constant is K. Here, use this second order reaction, rate constant is 0.54 per molar per second at 300 Celsius degree. Ask you, how long in seconds would it take for the concentration of NO2 to decrease from 0.6 to 0.28? For NO2 concentration decrease from 0.6 molar to 0.28 molar. How long it take? This is in seconds. And B, also you calculate half-life. Carry two concentration decrease from this value to this value. This means we need an integrated rate law. As I said during the class, if you are not very good at math or you never take calculus 3 differential equation, then you need to remember the integrated rate law. Rate law itself is a differential equation because the rate is d concentration over dt. Rate is d concentration. If A is a rectangle, Of course, we need to give a negative, right? dA over dt is a differential equation. So integrated rate law is the solution for this differential equation. For this case, here is this second order reaction, right? So this 2. And this negative because reactant concentration decreases with time. So integrated rate law is solve this equation, tell you what is a reactant concentration related to time. So this is the rate law. So integrated rate law for second order reaction. Since here reactant is angle 2, we just write angle 2 directly. Okay, this is a solution from rate law. We call this is integrated rate law. You need to remember. First order reaction, second order reaction. We have a table. It takes summarize integrated rate law for zeroth order, first order, second order. Second order could have one reactant, could have two reactants. For the two reactants reaction, second order not required. That is too complicated. Only one reactant. There's one reactant, right? Angle 2. That is the integrated rate law. And this angle 2, 0 means initial concentration. This is final concentration. So this is initial, this is final. Okay. So we just plug in the number. Here is initial concentration, 0.62. Final concentration, 0.28. Rate constant K, here is 0.54. If you remember this equation and plug into correct number from the one whatever I tell you, I would say you get most for this part because the rest is just pure mass. How to solve this T? So clearly you move this to left side. So this minus this is reciprocal. Then flip over. Well, no, divided by 0.54, right? So there is 0.28 minus reciprocal 0.62, 0.54 times T. Then both sides divided by 0.54. This is T. This T value will be unit will be second because this T is per molar per second and per molar cancel this. Then per second in denominator is second. Okay, so are you okay? So this is a show work. First, you need a general equation. Second step, plug into numbers and give to you. Then give answer. And you even don't need to show me this step. Just give me answer directly. It's fine. Okay. Necessary 3 steps. Okay. First 2 steps. More important than the last final answer. More important. Worth more for first 2 steps. Are you okay? Okay. Then V half-life. This is the A, right? Then B, half-life. For second order reaction, half-life depends on initial concentration, reciprocal of K times initial concentration. Right. And here also you calculate the half-life at these two concentrations. This means this concentration at this concentration. So half-life at 0.62. K is tell you 0.54. This is per molar per second. Times concentrating 0.62 molar. So molar concentration is per molar. Then per second in denominator, flip over is second. Right, use calculator. 1 divided by 0.54 divided by 0.62. This give you answer is 3 seconds. While half-life at 0.28 molar. For the K times A0. This give you 6.6 seconds. Are you okay for this? Okay. Then we have time to show you another one. Oh, only 40 minutes left. So probably this class we cannot start a new chapter. 40 minutes, show you another one. Then will be end of the class. Number 34. 34, the reaction is CO. React with Cl2. Produce COCl2 gas. At 250 degrees Celsius. Is 1,500 times faster. Then at 150 degrees Celsius. Also, you calculate activation energy. of the reaction. So tell you this reaction's rate is 1,500 times faster at 250 degree compared with at 150 degree. Also calculate EA. So clearly this is temperature effect, right, of reaction rate. So temperature effect of the reaction rate looks like this: K2 over K1 equal to EA over R times without this negative sign. This is T1 or T2 first. You need to be careful. Without this negative sign, then T1 first, T2 next. If you prefer use negative sign, then T2 first, T1 next. I prefer use this, either way. Okay. So just be careful, their order. Okay. This is most important. If you remember this formula, if this is 10 points, problem solving, I may give you 3 points already. Important, because next is according to this. So K1 is a rate constant at T1. K2 is a rate constant at T2. Okay. Then what is K1? What is K2? And what is T1? What is T2? So you need to rate this. This reaction, the rate at 250 degrees Celsius is 1,500 times faster than at 150 degrees Celsius. Okay. If you think 150 is T1, then 250 is T2, right? Then this only tell you K1, K2 ratio is K2 is 1,500 times faster. Then tell you actual number. So from here, K2 is 1.5 times 10 to the third power fast of K1, right? This means 1,500 times faster. If you write this, K2 is 1,500 times faster than K1, then T2 is 250 degrees Celsius. Be careful. You cannot plug in 250 here directly, because this R is more per Kelvin. You need to use Kelvin. So you need to convert it to Kelvin. You can use 273. If you remember 0.51 is perfect. If you don't remember 0.51, it's fine. But you must plus 273. And that's key. So it will be 523.15 K, right? Then T1 clearly is 150 degrees Celsius, which is 150 plus 273.15 K is 423.15 K. Now just plug into this formula. So log K2 over K1, the K2 is 1 times 10 to the third power K1 over K1. So K1 will be cancelled. Then EA. During the test, I will tell you our gas constant. Okay, don't worry. Gas constant is 8.314 joule per mole per K. Then times T1 reciprocal. T1 is this 423.15 K. T2 the 523.15 K. So K1 cancel a pure number. This K cancel this. This K cancel this per K. Okay, left over. This EA should be joule per mole. Okay, anyway, if you can plug into correct number in this formula, become this, then you get most. Because the last step just give answer of EA. Okay. So EA will be 1.35 times 10 to the fifth power. So it should work. It's three minimal steps. First, general equation. Second, plug into necessary numbers. Leftover one, you want to solve it, right? Then last step, give answer. This is necessary work. Do you know how to solve this equation? Solve this equation for EA. First, use calculator, find this, right? Then this divided by 8.314. You get an answer. Then use calculator, take natural log of 1,500. So this number, you can see this way. This number times 8.314. Then divided by this number in the parentheses. Anyway, this is a pure math. Okay, so if you want, I can show you more. So log of 1,500, the actual number is 7.31. Then right side, EA over 8.314. These two subtract, use calculator. These two subtract, you get a number is 4.52 times 10 to the negative 4. Then EA equals to 7.3431 times 8.314 divided by 4.52 times 10 to the negative 4, right? So both sides multiply by this, then both sides divided by this, right? You get the final answer. Okay. And only 4 minutes left. Are you okay for this? Are you okay for this one? Yeah, only 3 minutes left. Do you have other questions?